Hello, everyone. This is my MSDS 692 Data Science Practicum 1. And the title of this practicum is Forecasting Electricity Demand with Python Programming Language. My table of content starts with an introduction, problem statement, data source, import libraries, EDA, recursive autoregressive forecasting, forecasting with exogenous variables, direct multi-step forecasting, and finally a conclusion. I do have a project plan, which is a time series. A time series is a sequence of chronological ordered data spaced at equal or unequal intervals. The forecasting method predicts a time series future value by modeling it based on its past behavior, which is autoregressive, or by using other external variables. Problem statement. The data set is a time series with electricity demand in megawatts for the state of Victoria, Australia, from 2011 to 2014. It's available for this project. Demand for electricity in Australia has been in the spotlight for the general population due to the recently increasing price. Still, forecasts of electricity demand have been expected to decrease due to various factors. The project aims to generate a forecasting model capable of predicting the next day's energy demand at the hourly level by accurately predicting monthly electricity demand. The proposed project design will be achieved using a time series forecasting with skit-learn regressors. And the data source was downloaded from GitHub for this project. The dataset contains 5 columns and 52,608 complete records. The information in each column includes the time, the date, the demand, temperature, and the holiday. And also, I listed the libraries that I used to perform my modeling and forecasting in Python here in this very slide. I move on to look at the predicting monthly electricity demand, looking at the trend from the data set. The graph shows that electricity demand has annual seasonality. Also, there is an increase centered on July and very accentuated demand peaks between January and March. Section of the electricity demand time series. When zooming in on the time series, a clear weekly seasonality is evident, with higher consumption during the work week, which is basically Monday to Friday, and a lower consumption on weekends, which will be a Saturday and a Sunday. It is also observed that there is a clear correlation between the consumption of one day and that of previous day. I do have a box plot explaining the electricity demand distribution by month. From my box plot graphics, it is observed that there is an annual seasonality with higher median demand values in June, July, and August, and with high demand peaks in November, December, January, February, and March. I also look into the demand distribution by weekdays. Weekly seasonality shows lower demand values during the weekend. And I have a Vowling plot that shows the trend in holidays and non-holidays. Holidays tend to have lower electricity consumption in Victoria, Australia. I also look into the partial autocorrelation from the two graphs. The autocorrelation and partial autocorrelation plots show a clear association between 1 hour's demand and previous hours, as well as between 1 hour's demand and the same hour's demand on previous days. This type of correlation is an indication that autoregressive model can work well for the forecasting. I also look into the correlation between electricity demand and temperature in Victoria, Australia. The scatter plot helps us to visualize the relationship between the two variables. High demand occurs when temperatures are high because of air conditioning, but there's also a heating effect where demand increases for very low temperatures. That was very interesting. And I do have a line plot to look into the pattern of mean yearly energy demand by hour of the day. From the visualization, we can see that the mean yearly energy temperature by hour of the day was highest in year 2013 at 0700 hour at a temperature greater than 24 Celsius. Then we go into our model, starting with the recursive autoregressive forecasting. It's a model, the model is created and trained from a linear regression model with a ridge, penalty, and a time window of 24 lags. The latter, for each prediction, the demand values of the previous 24 hours are used as predictors. And the backtest error matrix explains how the model would have behaved if it had been trained with the data from 2012 to 2014 at 23:59 hour each day. The following 24 hours were predicted and evaluated, and the backtest error result was equal to 289.5. Then we went on to do an hyperparameter tuning to recognize the best combination of lags, a grid search with validation by backtesting the data was employed in this forecast. In the trained forecaster autoreg object, the first 24 lags and a ridge model with the default hyperparameters are being utilized. The best results are obtained. Backtest with with test data, and once the best model has been identified and trained, its error in predicting the test data is calculated. After optimizing the lags using the best result from the configuration and the hyperparameters, I observed that the prediction error was reduced from 289.5 to 251.9 using the backtest metric error. Prediction intervals. The predicted interval has a lower coverage than expected, which was approximately 80%. This may have been due to high error made by the model for the days predicted on days 21, 24, and 25. These days are within the Christmas holiday period, usually characterized by a different consumption behavior than the rest of the month. We move on to forecasting with exogenous variables, which these are basically known variables. We use variables whose feature value is known and serve as additional predictors in the model. For example, holidays, the month of the year, day of the week, and time of the day. And by using the known variables, the prediction error is slightly reduced from 394.5 to 375.1 when we did the prediction. The new predictors further reduce the model error with a backtest error equal to 311.3. Also, we move on to direct multi-step forecasting, which is our last model that we performed on this very data set. when we forecaster refitted using the best found lags and parameters, and the whole data set lags were 1, 2, 3, 23, 24, 25, 47, 48, and 49. And the good thing about the direct multi-step forecasting was that the model follows a recursive prediction strategy in which each new prediction builds on the previous one. Then we have an anticipated daily forecast, the backtesting process, including the new exogenous variables, was repeated. In this case, using a gradient boosting LGBM regressor model, the direct multi-step strategy generates better results than the initial recursive strategy with a linear model. The backtest error is equal to 228.2. Actually, the backtest error on this very the anticipated daily forecast was better off than when we tried the recursive model. And finally, to my conclusion, in this project, I used time series data with electricity demand measured in megawatt for the state of Victoria, Australia, from year 2011 to year 2014 to generate a forecasting model that predicts the next day's energy demand at the hourly level. I started with an EDA analysis in order to explore the characteristics of our data set. In data cleaning process, null values were replaced with mean value, and some attributes are extracted since they were redundant. Hourly electricity demand are aggregated to daily level, so we can see the trend and seasonality functions more clearly. The data set is split into two sets, train and test, in order to train the models and test our results. And finally, I do put a table here on the last slide where it shows that direct multi-step forecasting using the LGBM regressor model ended up with a backtest error of 228.2 compared to recursive autoregressive with a 394.5 and a forecasting with exogenous variables with 311.3. The direct multi-step forecast had the lowest backtest error. And this comes to the conclusion why I figure out from this project that the direct multi-step forecasting LGBM regressor model is the best. Thank you.